Magnetization and magnetic intensity. We have seen that a circulating electron in an atom has a magnetic moment. In a bulk material, these moments add up vectorially and they can give a net magnetic moment which is non-zero. We define magnetization of a sample to be equal to its net magnetic moment per unit volume. M is equal to M net divided by V. So M is a vector with dimensions length inverse into ampere and is measured in a unit of ampere into meter inverse. Consider a long solenoid of n turns per unit length and carrying a current I. The magnetic field in the interior of the solenoid was shown to be given by B naught is equal to mu naught into n into I. If the interior of the solenoid is filled with a material with non-zero magnetization, the magnetic field inside the solenoid will be greater than B naught. The net field in the interior of the solenoid may be expressed as B equals B naught plus Bm, where Bm is the field contributed by the material core. It turns out that this additional field Bm is proportional to the magnetization of the material and is expressed as Bm equals mu naught into m, where mu naught is the same constant permeability of vacuum that appears in Biot-Savart's law. It is convenient to introduce another vector field H called the magnetic intensity, which is defined by H is equal to B by mu naught minus m, where H has the same dimensions as m and is measured in units of ampere into meter inverse. Thus, the total magnetic field B is written as B equals mu naught into H plus m. The contribution to the total magnetic field inside the sample is divided into two parts. One, due to the external factors such as the current in the solenoid, this is represented by H. The other is due to the specific nature of the magnetic material, namely M. The latter quantity can be influenced by external factors. This influence is mathematically expressed as M is equal to X into H, where X, a dimensionless quantity, is appropriately called the magnetic susceptibility. It is a measure of how a magnetic material responds to an external field. It is small and positive for materials which are called paramagnetic, and it is small and negative for materials which are termed diamagnetic. From B equals to B naught plus Bm and m equals to x into h, we get B equals to mu into 1 plus x into h, that is equal to mu naught into mu r into h, that is equal to mu into h, where mu r is equal to 1 plus x is a dimensionless quantity called the relative magnetic permeability of the substance. It is the analog of the dielectric constant in electrostatics. The magnetic permeability of the substance is mu and it has the same dimensions and units as mu naught. So mu is equal to mu naught into mu r, which is equal to mu naught into 1 plus x. The three quantities x, mu r and mu are interrelated and only one of them is independent. Magnetic susceptibility of some elements at the temperature 300 Kelvin are as shown. Example: a solenoid has a core of a material with relative permeability 400. The windings of the solenoid are insulated from the core and carry a current of 2 amperes. If the number of turns is 1000 per meter, then calculate A, H, B, M, C, B, and D. The magnetizing current Im. Solution: A. The field H is dependent of the material of the core and is equal to N into I, that is equal to 1000 into 2, which is equal to 2 into 10 to the power 3 ampere per meter. B. The magnetic field B is given by mu r into mu naught into H. Putting the values, we get the result as 1 Tesla. C. Magnetization is given by B minus mu naught into H divided by mu naught. Putting the values, we get the answer as 8 into 10 to the power 5 ampere per meter. D. The magnetizing current Im is the additional current that needs to be passed through the windings of the solenoid in the absence of the core, which would give a value as in the presence of the core. Thus, B equals mu r into N naught into I plus Im. Using I equals to 2a, B equals to 1, we get Im is equal to 794 amperes. Concepts. Number 1. What is magnetization? Magnetization M of a sample is equal to its net magnetic moment per unit volume. Number 2. What will a circulating electron produce? Solution: it will produce magnetic moment.